Before humanity, Earth was never silent. It was dominated for hundreds of millions of years by life forms so diverse, so specialized, that our species represents only an extremely recent fragment. If you shrink all of Earth's history down to 24 hours, humanity appears in the very last seconds. And before that moment, the world already belonged to others. Organisms that occupied every ocean, every continent, every available sky. Over about 3.8 billion years of life on Earth, humans have existed for only about 300,000 years. In other words, we represent less than 0.01% of the planet's biological history. Everything else is a world dominated by other life forms. And some of them were far more impressive than we imagine today. For more than 160 million years, dinosaurs held a dominant position on the continents. To give a sense of that duration, if all of human history were compressed into a single minute, the reign of the dinosaurs would last more than 2 hours. They were not a single species. They were a complete evolutionary explosion. Herbivores capable of reaching more than 30 meters in length, like certain sauropods, weighing up to 70 tons, more than 10 elephants combined. And predators like Tyrannosaurus rex, with a bite estimated at about 35,000 to 57,000 newtons, one of the most powerful ever measured in a terrestrial animal. But their dominance did not rely only on size. They occupied almost all terrestrial ecosystems: forests, plains, wetlands, coastal regions. Fossils show an exceptional diversity of behaviors: pack hunting in some species, sophisticated defense strategies, rapid growth in others. The Earth was not dominated by a single form, but by an entire network of complex ecosystems controlled by dinosaurs. And this reign was not isolated. In the oceans and in the sky, other forms of dominance already existed. In ancient seas, mosasaurs sat at the top of the food chain. Some exceeded 15 meters in length. Their jaws could open at an extremely wide angle, allowing them to swallow whole prey. In the sky, pterosaurs were the first vertebrates to master large-scale flight. Some, like Quetzalcoatlus, reached an estimated wingspan of more than 10 meters, comparable to that of a small airplane. And in even older oceans, ichthyosaurs had already adopted a form astonishingly close to modern dolphins. It's a powerful example of what is called convergent evolution. Different species that develop similar forms when faced with identical physical constraints, like speed in water. It shows one essential thing. Life doesn't repeat patterns. It reinvents them constantly. Then, about 66 million years ago, an event changes everything. An asteroid about 10 kilometers in diameter strikes Earth with an energy estimated at several billion times that of the Hiroshima nuclear bomb. The impact releases energy equivalent to tens of millions of megatons of TNT. The consequences are global. Planet-wide fires, darkening of the atmosphere, collapse of food chains. In just a few years, non-avian dinosaurs disappear. But dominance doesn't stop there. After this mass extinction, a new world emerges. And this time, mammals begin to occupy the niches left vacant. The oceans and the sky were never empty spaces. Long before mammals took their place on Earth, these environments were already dominated by entire lineages of predators, perfectly adapted to their surroundings. In the Mesozoic oceans, between about 252 and 66 million years ago, much of the food chain was controlled by marine reptiles. Among them, Mosasaurs represent one of the most impressive groups. Some reached more than 12 to 17 meters in length, the size of a modern bus. Their morphology is not that of a fish, but that of a reptile fully adapted to aquatic life, with a hydrodynamic body, limbs transformed into flippers, and a jaw capable of dislocating slightly to swallow large prey. Fossils found show that they occupied the position of apex predators, capable of hunting fish, ammonites, and even other marine reptiles. Before them, the oceans had already been dominated by ichthyosaurs, which appeared about 250 million years ago. Their shape is a striking example of convergent evolution. They closely resemble today's dolphins, even though they have no direct link to mammals. This similarity is explained by the physical constraints of the aquatic environment. To reach high speeds in water, natural selection consistently favors streamlined shapes that reduce hydrodynamic drag. Some ichthyosaurs may have reached estimated speeds of over 40 kilometers per hour, comparable to certain modern marine predators. In the air, another lineage completely dominates ecosystems: pterosaurs. They appear about 220 million years ago and represent the first vertebrates capable of powered flight. Unlike modern birds, their wing is based on a skin membrane supported by an extremely elongated finger. Some species, such as Quetzalcoatlus, reached estimated wingspans of between 10 and 11 meters, making them the largest flying animals known to date. At that size, their mass remains relatively low thanks to hollow bones and a body structure optimized for flight. Biomechanical analyses suggest that these creatures could soar over very long distances by exploiting thermal updrafts, much like today's large birds of prey, but on a scale several times greater. Their ecological role was major. Some were active hunters, others scavengers, contributing to the balance of aerial and coastal ecosystems. What is important here is to understand that these groups did not merely exist. They dominated entire environments for tens of millions of years. On the human scale, that represents an almost incomprehensible duration. Modern humans have existed for about 300,000 years, whereas these biological reigns lasted up to 50 to 100 times longer. The fossil record also shows one essential thing: such dominations are never permanent. They depend directly on global environmental conditions: temperature, sea level, atmospheric composition, resource availability. Each parameter influences the survival of these species. And yet, even in these worlds that were already fully structured, dominance was not limited to giant forms or those visible at the surface. Other life forms, far more discrete but just as essential, were already controlling the foundations of these ecosystems. After the disappearance of non-avian dinosaurs about 66 million years ago, a massive ecological vacuum set in on Earth. A mass extinction, probably triggered by the Chicxulub asteroid impact and amplified by intense volcanism, wiped out nearly 75% of existing species. For a time, ecosystems were completely disorganized. But that void does not remain empty for long. Mammals, until then small and often nocturnal, began to occupy the niches left vacant. In just a few million years, an impressive evolutionary acceleration occurs on a geological timescale. This phenomenon is called adaptive radiation, rapid diversification from a few survivors. It is in this context that what is known as the Cenozoic megafauna emerges. In the cold regions of the northern hemisphere, woolly mammoths appear. These animals could reach about 3 to 4 meters at the shoulder and weigh up to 6 tons. Their adaptation to cold is remarkable. A thick layer of subcutaneous fat, a dense coat, and tusks that could measure more than 4 meters long. They evolved in tundra and steppe environments, where temperatures can fall well below -30 degrees Celsius. Their survival depends on a fragile climatic balance, directly linked to the glacial cycles of the Pleistocene. In the same ecosystems, mastodons and primitive elephants are also found, belonging to distinct lineages. Their large body mass allows them to withstand climatic variations and travel long distances in search of food. Some species exceeded 5 tons, with highly specialized feeding strategies depending on the environments. In South America and Australia, other, even more surprising forms appear. Giant sloths, such as Megatherium, reaching nearly 6 meters long when standing upright, capable of feeding on tree vegetation. Their mass could exceed 3 tons. In these same regions, giant marsupials occupied niches similar to those of large placental herbivores elsewhere on the globe. But megafauna is not limited to herbivores. Extremely specialized predators also appear. Smilodon, often called the saber-toothed tiger, has canines that can reach up to 20 to 28 centimeters in length. Unlike modern felines, its morphology is adapted to fast, powerful attacks on large prey. Its recent extinction, around 10,000 years ago, is probably linked to a combination of climatic changes and human pressure. In some regions, hybrid carnivores also dominate ecosystems. Amphision, nicknamed the bear dog, combines characteristics from several lineages of modern carnivores. Some species could exceed 200 kilograms and exert significant pressure on local food chains. What links all these species is one simple thing. They are all the direct product of the climatic conditions of the Cenozoic. Cycles of glaciation and warming, the availability of plant resources, and variations in sea level continually shape their evolution. Paleontological data also show a constant. The more unstable environments are, the more extreme life forms become. Sizes increase, specializations intensify, and survival strategies become increasingly complex. But despite their visible dominance, these giants represent only part of the story, because the real structures that keep ecosystems functional are often invisible to the naked eye. Even if large mammals and predators visually dominate landscapes, they all rest on a much older and much more massive base. A layer of life that never truly disappears, even after extinctions, even after global catastrophes. That layer is insects and microorganisms. Insects today represent about 80% of all known animal species. Their dominance is not recent. It goes back more than 400 million years, long before the dinosaurs. Their evolutionary success rests on simple but extremely effective biological traits: small size, rapid reproduction, and an almost instantaneous capacity to adapt to environmental change. Some insect groups have life cycles lasting only a few days, which allows them to evolve at a genetic speed far greater than that of large vertebrates. Where a mammal takes tens of thousands of years to adapt to a climatic change, an insect population can evolve in a few hundred generations. At their scale, that sometimes represents only a few decades. In the fossil record, we already observe giant insects during certain periods such as the Carboniferous. Meganeura, a prehistoric dragonfly, could reach about a 70-centimeter wingspan. This exceptional size is directly linked to the concentration of oxygen in the atmosphere, estimated at more than 30%, compared with 21% today. This single biological parameter was enough to completely change the physical limits of terrestrial life. But beyond visible insects, there is another dominance even more fundamental: microorganisms. Bacteria appeared on Earth about 3.5 to 3.8 billion years ago. That means they have occupied the planet for almost 90% of its history, long before the appearance of plants, animals, or even oxygen in the atmosphere. They represent the oldest, most resilient, and most widespread form of life. It is estimated that there are about 5 times 10 to the power of 30 bacteria on Earth at any given moment. Their cumulative mass would be greater than that of all animals combined. They are present in the oceans, in soils, in deep rocks, in the atmosphere, and even in extreme environments such as hydrothermal vents or glaciers. Some bacteria, called extremophiles, can survive conditions we consider incompatible with life. Temperatures above 100 degrees Celsius, crushing pressures on the ocean floor, a total absence of light, or highly acidic environments. This directly challenges the idea of an ideal environment for life. Geochemical data also show that bacteria have profoundly modified the planet itself. For example, the oxygenation of the atmosphere about 2.4 billion years ago, called the Great Oxidation, is directly linked to their photosynthetic activity. Before this event, Earth's atmosphere was toxic to most forms of life today. In other words, microorganisms are not just one form of life among others. They are a planetary engine. They regulate the cycles of carbon, nitrogen, and oxygen. They influence the composition of the oceans, soils, and even the global climate. Without them, large animals, including humanity, could never have existed. Modern ecosystems, therefore, rest on an invisible structure at the human scale. An inverted biological hierarchy. The smaller the organisms, the greater their global impact. And that is where the paradox lies. What we perceive as dominant on Earth, animals, predators, the giants of the past, is in reality only a thin layer on the surface of a system controlled by invisible life forms. Life forms that have survived all known mass extinctions, and that are probably the planet's true heirs. What links all the dominant species in Earth's history, from dinosaurs to giant mammals, from marine predators to giant insects, is a constant that geological data confirm unambiguously. No biological dominance lasts forever. Over the 4.5 billion years of Earth's history, at least 5 major mass extinctions have been identified. Each time, between 50% and 90% of species disappear in a relatively short time on the geological scale, sometimes in just a few thousand years. The best known, the end Cretaceous extinction, about 66 million years ago, is associated with the impact of the Chicxulub asteroid. The energy released is estimated at about 10 to the 23rd power joules, several billion times the combined power of all current nuclear weapons. This event triggered global fires, a dust cloud blocking sunlight for months, and a massive collapse of food chains. But that is only one example among others. The Permian-Triassic extinction, about 252 million years ago, is even more destructive. Up to 96% of marine species and around 70% of terrestrial species disappear. Probable causes include massive volcanism in Siberia, releasing enormous quantities of CO2 and methane, leading to abrupt global warming and ocean acidification. These events show a simple but brutal reality. Life on Earth does not evolve in a stable environment. It evolves in a system punctuated by global catastrophes. And yet, after each extinction, life returns. That return never happens in the same way. The dominant species of an era vanish almost entirely, making room for new lineages. This is a mechanism called adaptive radiation. The survivors exploit the ecological niches left vacant and diversify rapidly. This is exactly what allowed mammals to replace the dinosaurs, and later primates to develop much later. But this cycle implies an essential consequence. Biological dominance is always temporary. Even the most adapted, the largest, the fastest, or the most intelligent species end up being replaced when conditions change violently enough. Fossil data also show that so-called dominant species are not necessarily the most numerous, nor the most important for the overall stability of ecosystems. They are often visible, but not central. Microorganisms, on the other hand, make it through every crisis without ever disappearing completely. This creates an implicit hierarchy in living things. The most visible forms are often the most fragile in the long term, while the invisible forms are the most stable across vast timescales. And that is where Earth's history takes on a more unsettling dimension. Humanity appears about 300,000 years ago. On the scale of 3.8 billion years of life, that represents less than 0.01% of the planet's biological history. And yet, in an extremely short time, the human species becomes a major geological factor. Current data show that human activities are altering the carbon cycles, accelerating species extinctions, and transforming landscapes at a pace unmatched since past major natural catastrophes. Some scientists already speak of a possible sixth mass extinction. But one point remains essential. In all previous extinctions, life continued. The question, then, is not only which species dominate, but rather which forms of life survive extreme changes in the Earth system. And so far, the answer is constant. The simplest, oldest, and most adaptable forms of life always remain present. Biological empires change. Dominant species disappear. But life itself persists. And that may be the only true constant in Earth's history. If we widen the timescale even further, one idea becomes hard to ignore. Biological dominance is never more than a snapshot. Fossils show us that entire species appear, prosper for millions of years, then disappear without leaving direct descendants. On the human scale, 1 million years is already a nearly incomprehensible duration. Yet in Earth's history, it is sometimes an extremely short phase. Let's take a simple order of magnitude. Non-avian dinosaurs dominated Earth for about 160 million years. Humanity, by contrast, has existed for about 300,000 years. That means dinosaurs occupied the planet about 500 times longer than our species has existed. And yet, they too disappeared. Geological data indicate that their extinction is not linked to a biological weakness, but to a sudden external event, the Chicxulub impact. A disruption so rapid that ecosystems did not have time to adapt. Food chains collapsed in cascade, from phytoplankton up to the large predators. This mechanism is crucial. In mass extinctions, it is not the weakest species that disappear, but those whose survival depends on an ecological network too complex to withstand a global shock. And that completely changes how we read. Dominance. A dominant species is not necessarily the most resilient. It is often simply the best adapted to a specific context, as long as that context remains stable. Yet climate archives show that Earth is rarely stable over very long periods. The quaternary glacial cycles, for example, show global temperature variations of several degrees in just a few thousand years. On the geological timescale, that is extremely fast. Fast enough to completely redistribute habitats, shift species ranges, and rewrite ecosystems. In this context, survival is not a question of superiority, but of flexibility. Some biological lineages illustrate this principle perfectly. Sharks, for example, have existed for more than 400 million years. They have survived several massive extinctions without fundamentally changing their body plan. Their effectiveness does not come from total ecological dominance, but from an extremely stable and adaptable biological structure. Conversely, many species that were dominant in their time disappeared without leaving any direct evolutionary trace. This suggests one important thing. Earth does not favor the permanence of complex forms, but the continuity of systems capable of adapting. And this also applies to invisible forms of life. Microorganisms, for their part, have never stopped existing. They do not need large ecological structures to survive. They can mutate quickly, colonize new environments, and exploit almost any available energy source. Scientific estimates show that they probably represent the majority of the planet's living biomass by total mass, even though they are invisible to the naked eye. This contrast is fundamental. The more complex and specialized a life form is, the more it becomes dependent on a fragile balance. The simpler and more flexible it is, the more resistant it becomes in the long term. This is a complete inversion of our intuitive perception of strength. From this perspective, the dominant visible species of each era are not the true pillars of life. They are rather temporary expressions of a global ecological equilibrium. And that equilibrium is constantly changing. What dominates today has no guarantee of dominating tomorrow. The fossil record never shows a perfect continuity of dominance. It shows successions, replacements, collapses followed by reconstructions. And it is exactly this pattern that leads to a broader conclusion. Life on Earth is not a straight line, but a series of cycles. Cycles of stability, cycles of crisis, cycles of rebirth. And with each cycle, the actors change, but the system itself continues.
Flies, bees, butterflies, dragonflies, cockroaches, bugs, crickets, beetles, stick insects. On Earth, there are a multitude of insects of all sizes, morphologies, and colors. Today, there are 1.3 million species of insect. That's 2/3 of all living organisms. Insects are everywhere on the planet, even in Antarctica, home to the tiny Belgica antarctica fly. This ubiquity is the result of a long evolutionary process. Their history goes back a long way. The first insect fossils date back over 400 million years. Insects arrived on Earth long before us, long before our ancestors, and even before the first mammals. In the course of their evolution, they managed to colonize numerous ecosystems. They colonized land, but also bodies of fresh and salt water, like the aquatic bug or halobates, the skating insects that surf the ocean waves. All insects, however different from one another, have one thing in common. They are small animals without vertebrae, with a body made up of 3 segments: head, thorax, and abdomen. Unlike mammals, they have no internal skeleton, but an external skeleton called the exoskeleton, which serves as their carapace. Insects are often said to have multiple brains. Indeed, while they have a main brain in the head like us, they also have multiple cerebral ganglia in every other segment of their body. Each limb is thus managed by its own mini-brain. Insects are therefore extremely reactive and can easily evade their predators. Perhaps this is one of the reasons why they have survived 400 million years of evolutionary history. Another feature common to many insects is their metamorphosis. Flies, butterflies, and dragonflies go from larva to adult by metamorphosing in a cocoon. Other insects, such as grasshoppers, cockroaches, and locusts, molt. With each molt, their organs gradually develop until they finally reach adult size. Insects are fascinating animals. Crickets and grasshoppers can perceive ultrasound that our ears can't pick up. Bees perceive radiation in the ultraviolet spectrum. Notonectus, a kind of water bug, perceive polarized light. And there are certain insects we don't yet know well, whose sensory capabilities are beyond imagination. The Earth is home to a huge variety of insects of all sizes. The smallest insect, a tiny parasitoid wasp, measures barely 1/10 of a millimeter. Other insects, however, are much larger. Some butterflies can measure up to 30 centimeters or 12 inches wingspan. The Atlas butterfly, the world's largest insect, covers an area of 160 square centimeters with its wings. The wingspan of the South African white witch can reach 35 centimeters or 13 inches. Giant stick insects found in Asia can measure over 50 centimeters or 20 inches in length. For a long time, the record for the longest insect was held by a Malaysian stick insect measuring 56.7 centimeters or 22 inches, kept at the Natural History Museum in London. This record was broken in 2016 when entomologist Zhao Li discovered a 62.4 centimeter or 24.5 inch long phasma in China. There are also some particularly massive insects such as beetles. The world's heaviest insect is the Goliathus goliatus, a beetle that lives in the equatorial forests of Africa. Its larva weighs between 80 and 100 grams, 4 times more than a canary. The Titan, a beetle living in the Amazon rainforest, can reach 16 centimeters or 6 inches in length. But all this is nothing compared to the dimensions of giant carboniferous insects. Today, these giant insects no longer exist. But why not? How can we explain the impressive size of certain insects over 300 million years ago? How did they appear, and how did they disappear? What did the Earth look like at the time of the giant insects? To answer all these questions, we're going back over 300 million years of history to explore the Earth in the Carboniferous, the golden age of insects. Are you ready to go back in time? Our journey begins now. understand this, we need to go back several 100 million years. It may come as a surprise, but butterflies and bees belong to the same group of species as crabs, shrimps, and lobsters, the arthropod phylum. In fact, it's not all that surprising when you think about it. Like insects, crustaceans have an articulated exoskeleton. This means that the hard part of the skeleton is on the outside of their body, and not, as in mammals, on the inside. A bit like a carapace. In arthropods, this carapace is largely composed of chitin, a carbohydrate close to cellulose. In terrestrial species such as bees and chafer beetles, it is tough but flexible. In aquatic species such as crayfish and crabs, it is harder, as it is calcified. As they grow or metamorphose, arthropods must shed their shells, which have become too small. This is called molting. Crabs, like butterflies, molt as they grow.
Comme les écrevisses et les crabes, elle est plus dure, car elle est calcifiée. Quand ils grandissent ou se métamorphosent, les arthropodes doivent se débarrasser de leur carapace devenue trop petite. C'est la mue. Les crabes, tout comme les papillons, muent lorsqu'ils grandissent.
Another thing insects and crustaceans have in common is that their bodies are made up of successive segments. There are more or fewer segments depending on the species. From each segment emerge pairs of appendages, antennae, mandibles, and legs. Insects are six-legged arthropods, but there are also eight-legged arthropods such as spiders and mites. Some even have 100 legs like the aptly named millipede.
Certains sont même dotés d'une centaine de pattes, comme le bien nommé mille-pattes.
Arthropods are a very ancient species. They appeared 540 million years ago. Today, many species are descended from arthropods. Taxonomists have established several sub-branches within the arthropod phylum. Insects which have 6 legs, such as bees, wasps, and ants, arachnids with 8 legs, such as spiders, mites, and scorpions, myriapods, including millipedes, crustaceans, including lobsters, crabs, and sobugs. Arthropods are considered to be the first animals to have emerged from the water to walk on land, even before amphibians, contrary to popular belief. Today, their descendants have demonstrated an extraordinary capacity for adaptation. They are capable of adapting to numerous ecological niches and enduring extreme living conditions. This has enabled them to colonize all ecosystems, from grasslands to deserts, forests, mountains, cities, the seabed. But it has also enabled them to colonize every continent, all the way to Antarctica. Arthropods thus represent 80% of animal biodiversity. Today's insects are descended from arthropods. What did they look like 400 to 500 million years ago? Here is an example of a well-known arthropod from that era, the trilobite. This arthropod, which resembles today's woodlice, lived on the ocean floor between 550 and 250 million years ago. In the Paleozoic, from the Cambrian to the Permian, trilobites were abundant under the seas. There were over 20,000 different species. They left behind a wealth of fossils. The trilobite is a fascinating animal. Like today's flies, its eyes are multifaceted and can see 360 degrees. A great asset for escaping predators. This Cambrian arthropod feeds on mollusks and small trilobites. It's called Sydnea. Small in size, it could measure up to 13 centimeters or 5 inches, depending on the individual. Like the trilobite, this small arthropod is very abundant in Cambrian seas, It's Morella. It's even smaller than Sydnea, measuring between 2.4 and 25 millimeters. It's easy to recognize with its horseshoe-shaped cephalic shield and two antennae. Like Morella, the small arthropod, Yohia tenuis, has a cranial shield. What makes it special? Its 13 tergite plates, which form a carapace. This small arthropod, 7 to 23 millimeters, lives on sandy and muddy bottoms. Arthropods are also known as the first animals to leave the oceans and settle on land. 450 million years ago, animal life was still exclusively aquatic. Until then, only plants had succeeded in colonizing terrestrial environments. This colonization didn't happen overnight. In fact, it took millions of years for plants to emerge from the seas and settle permanently on land. During the Cambrian period, chlorophytic algae began to move from the seabed to continental wetlands. On land, algae seek out environments with similar properties to the aquatic worlds they have recently left behind. They settle in shallow freshwater. During the Ordovician period, between 485 and 444 million years ago, plants had to develop new characteristics to adapt to this foreign environment. Their walls thickened, protecting them from drying out. Their bodies became more complex, with the appearance of vascular tissues to facilitate the movement of liquids inside the plant, as well as stomata, small openings for gas exchange. Following the example of plants, animals also left the water to thrive on land. In the Silurian, between 444 and 419 million years ago, arthropods followed the path opened by plants a few million years earlier and began to colonize dry land. The first animals to take the plunge were myriapods, or millipedes. Like algae a few million years before them, they began by establishing themselves in terrestrial wetlands. But even though the conditions are similar to those in which they live, they remain more difficult than in river or marine environments. Like plants, arthropods will have to develop new characteristics to adapt to this new, harsher environment. Not only must they adapt their breathing and reproduction mechanisms, but they must also protect themselves from exposure to ultraviolet rays. And what about insects? When did they appear? When did the arthropod phylum split into several subphyla? At present, we don't know exactly. We have found no fossil record of the first insect to live on Earth. In other words, how insects evolved from arthropods remains a mystery to this day. However, by reconstructing the genetic evolution of today's insect species, we can estimate that the common ancestor of all insects appeared in the Silurian. The earliest known insect fossils date back 425 million years. These fossils are more recent than the first fish fossils, which date back 530 million years. It is therefore estimated that the first insects appeared after fish. But they are still older than the first fossils of dinosaurs or mammals, which date from 230 and 210 million years ago. Insects therefore appeared after fish, but before reptiles, dinosaurs, and of course human beings. The world's oldest complete insect fossil is 365 million years old. It is Strudiella, a small grasshopper-like insect. The fossil was discovered in the Belgian Strud deposit, which dates from the Upper Devonian. It confirms that insects probably appeared in the Silurian and that they were already living on land at that time. Insects did not appear underwater and then emerge from the seas to adapt to dry land. They appeared after the arthropods had left the water. Strudiella has no morphological features adapted to aquatic life, although it fossilized in a temporary pond alongside aquatic arthropods. Gradually, along with their cousins, the myriapods, insects began to invade land. By the Devonian, the period following the Silurian, they were already much more numerous. What did the first insects which lived in the Silurian and Devonian periods look like? Insects inherited many morphological features from their arthropod ancestors: exoskeletons, articulated limbs, compound eyes. In fact, they're all arthropods, but with a slightly different silhouette. Their body is divided into three parts called tagmas: the head, the thorax, and the abdomen. Let's look at each tagma in detail to better understand what makes an insect, and not an arthropod, myriapod, or arachnid. Let's start with the thorax. An insect's thorax has 3 pairs of legs, making a total of 6. 6 legs, not 8 like an arachnid, or even 100 like a myriapod. The first insects had no wings. This characteristic appeared later, around 320 million years ago. Today, most insects have 2 pairs of wings. In Diptera, such as flies and mosquitoes, only 1 pair remains functional. Let's move on to the insect head. The morphology of their heads depends on their diet. For example, beetles and locusts have mandibles that enable them to crush food, while butterflies have tongues and bees have salivary ducts. The first insects were vegetarian, or phytophagous. They fed on lichens, mosses, and organic debris. Today, phytophagous insects account for over a quarter of all described species. But not all insects feed exclusively on plants. There are also omnivorous insects, such as cockroaches, grasshoppers, ants. There are even insectivorous insects like dragonflies. Insects' heads are topped by eyes made up of several hundred facets, giving them extreme peripheral vision. These faceted eyes are a legacy of arthropods. Trilobites already had compound eyes, enabling them to see 360 degrees. These fascinating eyes are the subject of numerous scientific studies and models. Each faceted eye is formed by the juxtaposition of several hundred simple eyes, known as ommatidia. In beetles, there can be as many as 30,000 juxtaposed single eyes. The last part of the insect segmented body, the abdomen. The abdomen contains the viscera and reproductive organs. It's also where you'll find the insect's highly specific respiratory system. When they first emerged from the water, arthropods internalized their respiratory system to protect it from desiccation. Today, all insects have an internal respiratory system adapted to air breathing. This is one of the reasons for their small size. Like us, they don't have lungs, or like fish, gills. They do, however, have trachea, which bring air in gaseous form directly to organs and cells. In small insects, breathing is passive. In larger insects, however, breathing is partially active through contractions of the abdomen. In other words, insects will contract and relax the muscles of the abdomen and sides to exhale and expel air from the tracheae. Their flexible carapace is elastic, so it will return to its original shape once the muscles have been released, enabling them to inhale passively. As we have seen, insects originated directly on Earth from arthropods. They did not first appear underwater like their ancestors. Insects are therefore terrestrial animals with a respiratory system adapted to life in the open air. But in the course of their evolution, some insects became secondarily aquatic. This concerns 3% of all insects, notably water bugs and dikes. These insects need humid environments for the development of their larvae, for example. But nature always adapts in the end. In these few insect species, the respiratory system has evolved, acquiring tracheobronchia to adapt perfectly to aquatic life. While the Silurian and Devonian periods saw the appearance of insects and the development of their differentiated characteristics, it is the Carboniferous, the next period, that is considered the true golden age of insects. The Carboniferous succeeded the Devonian around 360 million years ago. This geological period was marked not only by the diversification of insects, but also by the appearance of giant insects. During this period, insects underwent what is known as evolutionary radiation, i.e., very rapid diversification. They dominated the Earth's animal biodiversity in the last 20 million years of the Carboniferous. Emerging lands were covered by sparsely populated rainforests, conducive to the diversification of animal species. These forests quickly became populated by centipedes, scorpions, and spiders, cousins of insects, but also by cockroaches and locusts. Insects diversified considerably. The forest belonged to them. In the early Carboniferous, there were no amphibians, reptiles, or mammals in these terrestrial environments. We have found very few fossils from the first half of the Carboniferous. But fossils from the upper Carboniferous tell us about the insect species present at that time. This omnivorous insect, for example, is called Tenoptilus frequens. It is closely related to today's orthopterans, i.e., crickets and grasshoppers. This fossil is another example of an insect found in upper Carboniferous rainforests. Its name is Miscoptera nigra. It had a wingspan of around 16 centimeters or 6.3 inches. It had a small head and a long triangular abdomen terminated by filaments. These two insects are very different from each other, but they are only a small example of the diversity of insects of this period. As the Carboniferous period progressed, insects became more numerous and diverse, but they also evolved very rapidly. Most of the insect lineages known today appeared during the Carboniferous. It was during this period that insects acquired many of the characteristics that distinguish them today from other animal species. Starting with molting. Insects began metamorphosing 350 million years ago. When they molt, they go from larva to adult, often via a chrysalis. This process enables them to shed their exoskeleton, which has become too small. During the Carboniferous, many insects also acquired wings. As early as the upper Carboniferous, several types of flight already existed, ranging from gliding to hovering. Some insects have 3 pairs of wings, like those of the Stenodictia genus, with a smaller pair at the front of the body. Others have wings of shapes unknown today. Some have wings with disruptive coloration, enabling them to blend into their environment. In others, one of the 2 pairs of wings has already acquired a secondary role, as is the case today in many insect species. Blatoids, for example, have a pair of wings that are not used for flight, but act as protective elytra. Scientists believe that at this point in their evolutionary history, insects were already able to make sounds by rubbing their wings together or against a part of their body, an adaptation that probably took hold gradually throughout the Carboniferous period. Today, some insect groups are more diverse than others. These include Coleoptera, Diptera, Hymenoptera, and Lepidoptera. Beetles account for 20% of all living organisms, excluding bacteria. No fewer than 400,000 species have been cataloged, including beetles, ladybugs, and chafer beetles. But there are probably many more, perhaps even millions. Diptera, such as flies, mosquitoes, horseflies, and midges, are also very numerous on Earth. Over 150,000 species have been recorded. The same goes for Hymenoptera, such as bees and wasps, of which there are now almost 120,000 species, and Lepidoptera, such as butterflies, of which there are around 160,000 species. These insect groups are particularly diverse as they have been able to adapt over the course of their evolution. But in the Carboniferous, the distribution of insect groups was not exactly the same. The three most common insect groups were Dictyopterans, Orthopterans, and Paleopterans. What do these insect groups correspond to? Dictyoptera are the distant relatives of today's cockroaches, termites, and praying mantises. They were the most common insects in the Carboniferous period, although there was little species diversity. Orthopterans, ancestors of today's locusts and grasshoppers, were abundant in Carboniferous forests and far more diverse than Dictyopterans. Like Orthopterans, Paleopterans, the relatives of today's dragonflies and damselflies, were very abundant and diverse. And what about giant insects? To which insect group did they belong? When did they appear during the Carboniferous? Were they numerous? The reality is very different from the myth. The Carboniferous is often described as the era of giant insects, but this idea is erroneous. In reality, only a few insects were large. The majority of insects were similar in size to our present-day species. Scientists even agree that among insects, only one species could be considered a giant insect. The other species, often mistaken for giant insects, were actually arthropods. This is a far cry from the idea that Carboniferous forests were overrun by a multitude of giant insect species. The reality is that small insects proliferated during the Carboniferous, while a few species took advantage of favorable conditions to grow in size. The majority of insects were no bigger than a centimeter. What revolutionized insect evolution was their unprecedented evolutionary radiation. Let's return to the giant insects of the Carboniferous. The only giant insect species described today is the giant dragonfly Meganeura. It had a wingspan of 70 centimeters or 28 inches, which is 6 times longer than a hummingbird. In fact, to give you an idea, its wingspan was similar to that of a bird of prey, like the European sparrowhawk, which has a wingspan of up to 80 centimeters or 30 inches. In fact, Meganeura probably weighed the same as this species of bird of prey, 150 grams. Impressive, isn't it? In any case, its large size was enough to impress Meganeura's prey. And that wasn't the only frightening feature of this giant dragonfly. With its hawk-like build, its 6-jointed legs covered with spines to better grip its victims, its mouth parts designed to bite, and its 360-degree all-seeing eyes, it had all the makings of a predator. Like today's dragonflies, Meganeura had 4 wings, but its flight was very different, according to the fossil record. Because of its large size, this insect probably used less frequent but more powerful wing beats to keep itself aloft. It certainly hovered to maintain altitude for long periods and save energy. Once it had spotted its prey, Meganeura could swoop down on it at an extraordinary speed of 70 kilometers per hour or 43 miles per hour. This enabled her to attack in flight. Meganeura fed on insects such as cockroaches, bedbugs, cicadas, beetles, mosquitoes, wasps, termites, ants. It has to be said that she was spoilt for choice. The ground was teeming with life and she had little competition in terms of size. The English naturalist Charles Darwin recounted that when he arrived in the then sparsely inhabited Bay of Rio de Janeiro, he couldn't sleep because the buzzing was so loud, even though his boat had dropped anchor some distance from the shore. So imagine what it must have been like during the golden age of insects in broad daylight, when insect activity was at its peak. Two other species are often described as giant insects, but are in fact arthropods. The first is Arthropleura, an impressively large species of millipede. Arthropleura could measure up to 2.6 meters or 8 feet long and 50 centimeters or 20 inches wide. This gigantic millipede crawled through the undergrowth of tropical forests in the late Carboniferous and early Permian periods. Unlike Meganeura, it was not a feared predator, being a vegetarian. At least that's what researchers think, having discovered traces of pollen in its fossilized digestive tract. But its appearance seems to show otherwise. Arthropleura is quite frightening, with its 2 claws on the front of its body and its very powerful jaw. The other species often mistaken for a giant insect is Megarachne cervini. Discovered in 1980, Megarachne cervini was initially mistaken for a giant spider, hence its name. It was later discovered that it was in fact an aquatic arthropod of the Eurypterid group. In other words, a sea scorpion. The size of Megarachne cervini is not so extraordinary for an aquatic animal, but it's still impressive. 35 centimeters or 14 inches long and 60 centimeters or 24 inches between the upper legs. By comparison, the Goliath tarantula, the largest spider currently known, measures just 30 centimeters or 12 inches. The same goes for the female Theraphosa, a dangerous spider living in the tropical forests of South America. These spiders are capable of eating birds and throwing stinging hairs that cause unbearable pain, but they are less massive than Megarachne cervini. Megarachne cervini's appearance is very similar to that of a tarantula, with its spherical abdomen and 15mm circular eyes set between 2 other eyes. No wonder the scientists got it wrong. These giant insects and arthropods are rare occurrences. Over geological time, we have found very few other instances of such gigantism. But then, how to explain such gigantism in a handful of arthropods? Scientists have looked into this question and come up with several explanations. The first cause of this gigantism, long known to be the main explanation, is oxygen levels. In the Carboniferous period, oxygen levels in the Earth's atmosphere were estimated at 35%. Today it stands at 21%, with an imperceptible downward trend. How does this affect insect size? Dragonflies have no lungs. They breathe through tracheae in their thorax and abdomen. The larger the dragonfly, the more oxygen it needs. In the Carboniferous period, there was enough oxygen available in the air for them to grow. In our time, with today's oxygen levels, a dragonfly as large as Meganeura could not survive. So that's what enabled insects to grow: abundant oxygen in a planet dominated by rainforest. Logically, it was the increasing scarcity of forests and the fall in oxygen levels that led to the disappearance of the dragonfly Meganeura and the millipede Arthropleura in the millions of years that followed. But this is not the only explanation. How else can we explain the fact that large dragonflies persisted into the Triassic period despite declining oxygen levels? Another reason why Meganeura was able to grow so large is that it had no predators. Flying reptiles and birds did not yet exist. They would not appear until the Mesozoic, more than 100 million years later. Let's not forget that flying insects were the first animals to acquire wings, a major advantage over their competitors. At the top of the predation ladder, Meganeura had a real advantage over other species, with abundant food, maximum oxygen levels, and no other winged predators to threaten its development. This combination of factors was never repeated, which explains why there were no other cases of such gigantism among insects, and why there are no giant insects today. After the disappearance of the giant insects, other species will in turn benefit from favorable conditions for their development. Reptiles, dinosaurs, then mammals. What was the Earth like in the age of giant insects? Let's delve into the past to find out what the environment was like for the giant dragonflies of the Carboniferous period. The Carboniferous followed the Devonian, a period that ended with a terrible mass extinction. Around 358 million years ago, a drop in sea oxygenation and major climatic variations led to the disappearance of 75% of all species. This crisis is now known as the Devonian extinction and is one of 5 major biodiversity crises in the history of geological time. The next period, the Carboniferous, was particularly rich in plant life. It was at this time that the first bark-covered trees appeared. The fossilization of these trees produced large quantities of coal, giving rise to the coal deposits that would later become so precious to us in the Industrial Age. That's why this period is called the Carboniferous. The Carboniferous lasted from around 359 to 300 million years ago. This period was marked by the merging of all continental masses into a single supercontinent, Pangaea. This was the result of the collision of several blocks, including Gondwana to the south and Laurasia to the north. As a result of this collision, an immense mountain range was formed, crossing Pangaea from east to west, the Hercynian chain. This process is known as orogenesis. Today, fragments of this Hercynian chain survive in isolated massifs in Western and Central Europe, such as the Massif Central, the Armorican Massif, the Vosges, and the Black Forest, the Iberian Massif. The fragments of this mountain range also form the bedrock of a longer mountain chain stretching from the Urals to the Appalachians in North America. Pangaea remained as such until the Triassic period, some 50 million years later. Surrounding Pangaea is a unique ocean, which scientists have named Panthalassa. This is not the only body of water on our planet. As the continental plates merged, an inland ocean was also formed, Paleothetis. Today, all that remains of this inner ocean is the Mediterranean Sea. At that time, strange as it may seem to you, the northern part of Pangaea was at the level of the tropics. The climate was therefore conducive to the development of wetlands teeming with life, the famous Carboniferous rainforests. Contrary to popular belief, the Carboniferous period did not see the appearance of the first forests. It was in the Devonian period that the first trees appeared, forming the first forests. But if the Carboniferous is such an important period in the history of trees, it's because it was during this period that trees diversified considerably. During the Carboniferous period, lush forests developed. Tropical forest environments experienced unprecedented growth. Carboniferous marshes, warm, humid swamps, were rich ecosystems conducive to the diversification of small animals that had left aquatic environments. They can be found everywhere, on seashores and deltas, on the banks of rivers and streams, in former riverbeds, in the valleys of mountain lakes. While today, 40% of continental plant and animal species depend on wetlands for their survival and reproduction, at the beginning of the Carboniferous period, this was the case for almost all species. Carboniferous rainforests are lush and diverse. They are very different from the forests found today in tropical areas of our planet. This major expansion of rainforests is not without consequences for the planet's atmosphere and temperature. The abundance of vegetation will lead to a drop in CO2 levels in the air. Oxygen levels rose, enabling the growth of insects and arthropods, and the Earth's temperature dropped, initiating an era of glaciation that lasted until the beginning of the Permian. These changes gradually led to the development of new types of trees, such as deciduous trees, which appeared in more temperate zones. During the 60 million years of the Carboniferous, forests underwent numerous development cycles, linked to regular episodes of subsidence and rising sea levels. Around 305 million years ago, the transition to a drier climate led to the collapse of the Carboniferous rainforest. This event is considered to be one of two mass extinctions for plants, along with an extinction that occurred in the Upper Permian. Gradually, the swamp forest disappeared, leaving behind a soil rich in organic matter, notably coal. All along the equator, the great coal-bearing forests form the future great coal fields of North America, Europe, and Asia. Today's coal deposits are nothing more than the sedimentary remains of ancient Carboniferous forests. The intense mining activity of the industrial era in the early 19th century revealed many fossils dating back to the Carboniferous period, enabling us to learn more about the flora and fauna of this fascinating prehistoric era. It was by studying plant fossils dated to the Carboniferous period that scientists concluded that the first forests had already appeared in Devonian times. The Great Rainforest did not yet exist in the Devonian, but it was during this geological period that all the elements necessary for their appearance were put in place. It was in the Devonian period that the first leaves, root systems, trees, and reproduction using ova appeared. In the Carboniferous, forest environments continued to evolve, and above all to diversify. What do Carboniferous rainforest trees look like? Most Carboniferous trees reproduced by spores, just like today's ferns. Although fern species from this period no longer exist, fossils show that they closely resembled the tree ferns now found in the southern hemisphere, such as Australia and New Zealand. Carboniferous tree ferns can reach several meters in height. For example, ferns of the Soronius genus can grow to over 5 meters in height. Their trunk, called stipe, was not made of wood, but of fronds and roots. For the record, the name Soronius comes from the Greek word for starling. It refers to the patterns found on the fossilized stipes of these tree ferns, which evoke the plumage of these birds. In the Carboniferous, ferns thrived in humid environments, colonizing the higher areas of swamp forests. But they weren't the only ones. Other plants are abundant in tropical forests. They reproduce by means of ovules and pollen grains, enabling them to grow on the periphery of wetlands. Seed plants already existed, but were very much in the minority until the end of the Carboniferous period. They were mainly represented by conifers, such as Walchia, the first conifers to appear in the Carboniferous. Unlike today's conifers, Walchia have no needles, but small cat's claw-shaped leaves, similar to those of some of today's Araucarias. Now extinct, the chordates group is similar to our modern conifers, with very long leaves, from a few dozen centimeters to 1 meter long, and a few centimeters wide. Their morphology varies according to the environment in which they grow. The smallest forms were found in swampy environments, while the largest chordates flourished in drier environments. Flowering plants, or angiosperms, had not yet undergone their great diversification, which would come 150 million years later at the beginning of the Cretaceous. Carboniferous flora is dominated by lycophytes, vascular plants that reproduce by spores, like ferns. Examples include lepidodendrons and sigillaria. Today's representatives of this class of plants are small, but in the Carboniferous period, lepidodendrons could reach heights of up to 40 meters. These plants are extremely fast-growing. In just 10 years, they can grow to 40 meters, or 130 feet. They are firmly anchored to the ground by a complex system of underground axes called stigmaria. Like lepidodendrons, sigillaria can reach 30 meters or 100 feet in height. These trees have a strange appearance as they branch very late, and only once or twice. Lycopophytes grow alongside lower plants such as calamites, close relatives of today's horsetails, and medullosa, ancestors of our cycads. Calamites have now disappeared. These plants lived in Carboniferous marshes, growing up to 10 meters or 30 feet tall. Closely related to calamites, plants of the genus Phenophyllum are small creeping plants found mainly in ground cover or on the trunks of trees in Carboniferous forests. Carboniferous flora is diverse, varied, and abundant, the ideal environment for the development of a rich and abundant animal life. The Carboniferous is a pivotal period in the history of animal life. Insects are not the only species to have undergone an evolutionary radiation and important evolutions. It was also during this period that the first amniotes, the ancestors of reptiles, birds, and mammals, emerged from the waters. Like plants and arthropods before them, amniotes developed characteristics that enabled them to live in this new environment, where conditions were very different from those in marine environments. These new characteristics will enable them to gradually adopt an exclusively terrestrial lifestyle. This period of transition from an exclusively aquatic to an exclusively terrestrial life is marked by the rise of amphibians, animals that are both terrestrial and aquatic. Amphibians are tetrapods, i.e. vertebrates with four-toed legs. Their ancestors were the Sarcopterygians, or flesh-finned fish, a group of fish that includes today's coelacanths and lungfish. Today, tetrapods are represented by amphibians, reptiles, birds, and mammals. Unlike insects, which all have 6 legs, today's tetrapods do not all have four-toed legs. Snakes, for example, lost their legs during evolution, but they are still tetrapods. The appearance of tetrapods in the Devonian period, around 370 million years ago, and their subsequent diversification in the Carboniferous period represent a pivotal moment in the history of animal life. The first amphibian tetrapods had proto-lungs. They lived in humid environments. Their legs and proto-lungs enable them to move and breathe in the shallow oxygen-poor swamps of the Carboniferous. When they venture out of the swamps, amphibians crawl. They don't yet know how to walk. Their legs are primarily fins. It's only after several million years and numerous evolutionary adaptations that they will be able to carry their bodies and enable them to walk. We don't have much information on early Carboniferous tetrapods. Between the end of the Devonian and the middle of the Carboniferous, i.e. between 335 and 360 million years ago, very few tetrapod fossils have been found. This period is known as the Roemer Gap, after the American paleontologist Alfred Sherwood Roemer, who was the first to notice this scarcity of fossils. However, we have found tetrapod fossils dating from before this period, as well as a wide variety of more recent fossils. scientists have concluded that the Roemer Gap was marked by a very strong diversification of tetrapods, enabling the appearance of new tetrapod groups, notably amphibians. While insects swarmed in the canopies and soils of Carboniferous rainforests, the wetlands of Pangaea were soon populated by a wide variety of amphibian species. The largest species, like today's crocodiles, live mainly in water, occasionally venturing onto dry land, where they crawl about with some difficulty. Smaller amphibian species are more at ease on land as they are less heavy. They are becoming increasingly comfortable out of the water. The microsaur, Tuditanus, measures around 24 centimeters or 10 inches. It looks like a reptile, but is actually an amphibian. Lightweight, it is at home on land, although it continues to live most of its life in shallow water. More imposing than Tuditanus, amphibians of the Pholodierpodon genus can measure over 4 meters or 13 feet in length. Equipped with legs, they can crawl out of the water. But it's in the aquatic environment that they're most at ease, with an eel-like swimming action. Underwater, Pholodierpodons are formidable predators. Like insects, amphibians benefited from abundant food and the scarcity of predators or competitors during the Carboniferous period. In particular, they feed on insects and arthropods, which are abundant in wetlands. They never really strayed far from marshy areas. Even though they could breathe out of the water and crawl, most tetrapods still depended on the aquatic environment to reproduce and lay their eggs. Just as insects acquired wings or began to metamorphose, some tetrapod species underwent new evolutionary adaptations as early as the Carboniferous period. One example is the amphibians of the Phlegethontia genus. In these meter-long amphibians, the legs progressively reduced in size before disappearing altogether. Among the tetrapods, one group in particular was to evolve rapidly towards an exclusively terrestrial lifestyle, the amniotes. Soon, amniotes no longer needed water to lay their eggs. They were able to reproduce, feed, and travel exclusively on land. The first amniotes were the ancestors of dinosaurs, birds, reptiles, and later mammals. Unlike tetrapods, their bone structure and musculature enabled them to carry their entire body with their legs, allowing them to move around by walking. Thanks to the amniotic egg, fitted with a watertight shell and filled with liquid, they can now lay their eggs out of the water. The first amniotic eggs had a soft wall, much less solid than today's bird eggs. We have therefore not found any fossils of these eggs, but we can estimate the date of appearance of the amniotic egg by tracing the history of species that inherited this common trait. Two groups of amniotes quickly emerged. They are the ancestors of all non-amphibian tetrapod groups. Sauropsids, like Hylonomus laeli, a small insectivorous amniote 20 centimeters or 8 inches long, are the ancestors of reptiles, dinosaurs, and birds. Synapsids are the ancestors of mammals. Adaphosaurs were among the first vertebrate animals to be vegetarians. They occupied a previously vacant ecological niche, which enabled them to diversify considerably. But not all synapsids are vegetarians. Sphenacodontids, like Dimetrodon, are super predators, preying on prey of their size, such as adaphosaurs, but also fish-eating amphibians. Amniotes are adapted to life out of water. They will therefore be little affected by the collapse of the Carboniferous rainforest, the crisis at the end of the Carboniferous that caused the disappearance of many amphibian species. While plants and insects had already conquered dry land, much of the animal life of the Carboniferous was still aquatic. Like rainforest soils, seas and oceans teem with life, and species diversification continues. The super predators of the Devonian have disappeared, and calm has returned beneath the oceans. Because in the Devonian, aquatic life was rather turbulent, with fearsome predators, placoderms. Placoderms replaced the giant eurypterids of the Silurian as the most fearsome marine predators. Eurypterids were marine scorpions that could grow to over 2 meters in length. Placoderms are even scarier. They were the first vertebrates to develop a jaw. Their jaws are not equipped with real teeth, but rather with bony protrusions like the jaws of today's turtles. However, this is enough to crush their victims. The Dunkleosteus, for example, has more bite power than any fish or shark, including the great white shark. With its jaw, it can exert a pressure of up to 55 megapascals, rivaling our modern-day crocodiles. And that's not all. It can open its mouth in 1/50th of a second and measures 4 meters or 13 feet in length. Placoderms were super predators that reigned supreme in the Devonian seas. Fortunately, their reign was not to last long. By the Carboniferous, these cartilaginous fish had already disappeared. Other, less frightening predators appeared, such as ammonoids, distant relatives of ammonites. They feed on small marine animals such as mollusks and crustaceans. The return to calm is also an opportunity for other species to evolve and diversify. During the Carboniferous period, the Chondrichthyan class really took off. Chondrichthyans are the ancestors of our sharks and rays. Chimeras, such as Eniopora, also belong to this class of marine animals. Today there are very few chimera species, but they were abundant in Carboniferous seas. They were unique in that they fed by sucking up their prey. Unlike today's chimeras, which crush the shells of the animals they have sucked up, Carboniferous chimeras were not able to do this. However, they already possessed a number of crushing-related traits, which later developed and contributed to their survival under the oceans. Actinopterygians, or ray-fin fish, first appeared in the Devonian and survived the mass extinction of the late Devonian. During the Carboniferous, they too experienced an unprecedented boom. This group of ray-finned fish still exists today. They are particularly diverse, with around 30,000 species. In comparison, there are only 6,500 species of mammals on Earth. Coral reefs proliferated in Carboniferous seas. Corals of all kinds, in colonies or solitary, carpeted the seabed, creating an environment conducive to the development of species such as brachiopods, or bivalve-shelled animals, echinoderms, such as sea cucumbers, starfish or sea urchins, and mollusks such as mussels, cockles, or oysters, abundant in warm Carboniferous seas. Arthropods, on the other hand, are beginning to decline, starting with trilobites, once so abundant under the seas and oceans. $305 million years ago, the transition to a drier climate led to the extinction of many plant and animal species. This event is known as the Carboniferous rainforest collapse. It was one of the 2 greatest extinctions of continental flora in Earth's history. The second came 55 million years later, with the Permian-Triassic extinction. This crisis followed a period of aridification of the climate, which led to the drying up of the wetlands of Pangaea. During the Carboniferous period, trees flourished with their feet in the water. This climatic upheaval had a devastating effect on forests, which were totally dependent on a warm, humid climate for survival. In just 10 million years, almost half of all plant families will have disappeared. What caused the wave of glaciation that swept across southern Pangaea? In fact, it was the abundance of forests themselves that caused their loss. Forests have the capacity to capture and store CO2. In France, forests cover 31% of the territory and naturally absorb 10% of the country's CO2 emissions. In the Carboniferous period, the significant growth of forests helped to reduce the concentration of carbon dioxide in the atmosphere. This in turn reduced the greenhouse effect, leading to a general cooling of the Earth's climate. Trees are not the only ones to consume CO2. Mountains, newly formed by the collision of continental plates, will begin to erode under the action of water, a process that consumes enormous amounts of CO2. Glacial striations found in rocks from South Africa and Brazil show that during the Carboniferous, the southern part of Pangaea was covered by glaciers. In some parts of the continent, the ice cover is so thick that it reaches several hundred meters in thickness. The global drop in temperature led to the collapse of the rainforest so characteristic of the Carboniferous, but this was not the only consequence. Temperate zones appeared between the north and south of Pangaea, allowing the development of deciduous trees and new fern species, which competed with ferns with sporangial leaves. These new ferns carry seeds protected by an ovary, which are better protected than the spores of tropical tree ferns. But above all, these seeds are more accessible to pollinating insects. This was the beginning of flowering plants, or angiosperms, which would invade the planet a few million years later in the Cretaceous period. In fact, the trees that disappeared during this major crisis were those with large leaves, as their need for water increased. This is the case, for example, of lycophytes and calamites. The first conifers, on the other hand, were better adapted to dry environments, with their small leaves and reproduction by seed. During the 200 million years following the collapse of the Carboniferous rainforest, conifers spread across the globe. The cooling of Pangaea is accentuated by the albedo effect. The glaciation of southern Pangaea created ice caps. These great white expanses reflect sunlight instead of absorbing it. This will limit global warming by solar energy and accentuate the Earth's overall cooling. It is because of the albedo effect that today's melting ice is exacerbating climate disruption. Without glaciers to reflect sunlight, global warming will only accelerate. Contrary to what is happening today, the aridification of Pangaea led to a drop in global sea levels. Sea levels fell by several tens of meters, drying out wetlands. The first animals to feel the full impact of the drying out of the Carboniferous marshes were amphibians. Like the spore ferns, the amphibian population was to shrink considerably as the next period began, the Permian. The Permian lasted around 50 million years, between 300 and 250 million years ago. The crisis that hit plants once again benefited insects, which continued to diversify. Giant insects have not yet disappeared. Meganeura, the dragonfly with a 70 centimeter or 28-inch wingspan, can still be seen on the single continent. Although oxygen levels in the atmosphere have begun to fall, they remain fairly high during the Permian. But a new biodiversity crisis would put an end to the reign of the giant dragonflies. This major biodiversity crisis was triggered by intense volcanic activity. From the center of present-day Siberia, eruptions followed one another for almost a million years, releasing phenomenal quantities of lava, up to 3,000 meters or 10,000 feet thick. The Siberian traps, or piles of solidified basaltic lava, show that a total of more than 4 million cubic kilometers of lava flowed over Siberia. These eruptions will fill the atmosphere and oceans with toxic gases. These gases may even have fallen back to Earth in the form of acid rain. The oceans are suffocating, deprived of oxygen, and temperatures are rising. The ice caps that appeared at the end of the Carboniferous period disappeared, and the environment became hot and dry, with an average temperature of 19 degrees Celsius, or 62 degrees Fahrenheit. The Permian-Triassic crisis led to the disappearance of over 70% of terrestrial animal species and 95% of aquatic species. Among insects, the giant dragonfly Meganeura was unable to survive the sudden drop in oxygen levels. Beetles, such as the scarab beetle, took advantage of its disappearance to diversify in the next period, the Triassic. Wasps, bees, and flies also appeared at this time. In the Triassic, reptiles took advantage of the space vacated by Meganeura to colonize the skies. The era of flying reptiles began. As we have seen, giant insects will never reappear in the course of evolutionary history. In the Triassic, gliding reptiles, followed by flying reptiles, took the place left vacant by the giant dragonflies, a competition made all the tougher by the fact that they hunted the same prey. Oxygen becomes increasingly scarce, making it impossible for the lungless insects to grow in size. The ecosystem in which the larvae of giant dragonflies develop is completely transformed with the appearance of flowering plants. All these factors prevented the insects from once again reaching impressive sizes. Little by little, today's major insect orders were established. Beetles appeared in the Carboniferous 300 million years ago. In the Permian, 250 million years ago, Hymenoptera, with bees and wasps, and Diptera, with flies and mosquitoes, appeared in their turn. In the Jurassic, 150 million years ago, the order of Lepidoptera, with butterflies, took shape in its turn. In the Cretaceous, 100 million years ago, all the modern insect families appeared. Among vertebrates, it would take much longer. Insects played an essential role in the emergence of today's ecosystems. When flowering plants appear, pollinating insects such as bees and butterflies ensure their fertilization by transporting pollen from one flower to another. An unspoken bargain that also benefits insect pollinators who proliferated during the Cretaceous period and beyond, right up to the present day. Today, 90% of flowering plants are pollinated by insects. Numerous studies have shown the impact that the decline of pollinating insects would have on our health. Plant diversity would diminish, and with it dietary diversity, leading to nutritional deficiencies in humans. Pollinating insects aren't the only ones to help plants develop. In the soil, ants transport and bury seeds, helping plants to spread. Today, insects contribute to the balance of our ecosystems in a variety of ways. They contribute to the survival of a large number of species, serving as food for batrachians, spiders, and birds. Do giant insects still exist today? It's true that insects like Meganeura are not likely to reappear anytime soon. But some of today's insects are quite large, like the Bornean stick insect, certain butterflies such as the atlas, the Bombyx hercules, or the South African white witch, or the Goliathus beetle, which lives in savannas and equatorial forests. Some locusts can grow up to 10 centimeters long, like the giant weta, one of the world's heaviest insects, weighing between 30 and 70 grams. To breathe, insects use a network of tracheae, fine canals that branch out throughout the body and carry air directly to organs and tissues. The larger the insects, the longer and wider these channels need to be to meet their oxygen requirements. But that's not always possible. The diameter of the trachea is limited by the size of the opening between the legs and the body. Beyond this limit, the trachea can no longer expand, and the insect can no longer grow. Carboniferous insects were able to reach such dimensions because the atmosphere was richer in oxygen. Less air had to pass through the trachea to deliver the same amount of oxygen to their organs. Researchers have calculated that today, the maximum size an insect can reach at current oxygen levels is around 15 centimeters, which is exactly the record. And with the greenhouse effect, oxygen levels are not about to rise again. And that's not all. Larger insects are more exposed to predators. And today, unlike 300 million years ago, there are plenty of predators in the air. Bats, birds. So giant insects are certainly a thing of the past, which may not be such a bad thing after all. Small insects have survived until now, and will probably do so for a long time to come. It's not their small size that stops them. Ants can carry 1,000 times their own weight, and fleas can jump almost 340 times their own height, something that larger animals are incapable of doing, starting with man. In the end, perhaps the reduced size of insects is their real evolutionary advantage. The Triassic period spans around 50 million years, between 252 and 201 million years ago. It's relatively short compared with other periods of the Paleozoic or Mesozoic, but it's still a very long time span on the human scale. As you can imagine, over so many years on a planetary scale this time, there have been many changes. Put another way, it's 10,000 times 5,000 years, a period long enough to see many twists and turns. The Triassic, like previous periods, is divided into sub-periods. This division is necessary to better understand the various changes that take place, and ultimately, the history of the period as a whole. There is the Lower Triassic, the Middle Triassic, and finally, the Upper Triassic. Each of these periods is marked by a major change and a particular dynamic. The Triassic is, so to speak, a play in 3 acts. From 252 to 245 million years ago, the first act of our play, the Lower Triassic, laid the foundations for a new world that took hold during the Mesozoic. It itself comprises 2 sub-periods, 2 important scenes, if we remain in the register of theater: the Indusian and the Olenekian. Some species became extinct, others took their place, and all this took place in a very specific climate and world geography. During the Middle Triassic, the second act of our play, which runs from 245 million to 228 million years ago, we see the Triassic world expand, diversify, and enrich itself with new species and ecological niches. It too is made up of 2 stages, 2 sub-periods, called Anisian and Ladinian. Finally, the Upper Triassic, from 228 to 201 million years ago, is the last act of this play. It closes the chapter on the unprecedented upheavals that take place on the scene. Indeed, while a number of species seem to be stable and expanding throughout the Middle Triassic period, new events are about to shake up the existing scenario. This Upper Triassic period is divided into three scenes, three distinct subperiods: the Carnian, the Norian, and the Retian. While each of these scenes is of course important to our story, to simplify matters we'll refer to acts rather than scenes, i.e., the Lower, Middle, and Upper Triassic periods. To fully grasp all the issues at stake in the Triassic period, we need to keep each of these acts in mind and understand what defines them. The Triassic period saw a diversity of animal species during its course. In fact, life flourished to varying degrees during the period. The Lower Triassic, for example, the first act of the Triassic era, is a key stage in history. It symbolizes the renewal of life on Earth and in the saline waters of the globe. It corresponds to a period that could be described as transitional. The living world must gradually recover from the ordeals it has been through. After such a crisis, ecosystems are completely destroyed. The beginnings of the Triassic period were very difficult, and the Triassic Earth was far from being a prosperous and happy place. During the Paleozoic, as we've seen repeatedly on our travels, mass extinctions invariably closed the doors on previous worlds. The Earth will never again be as it was. But as the years go by, it reinvents itself and nature awakens anew. Time does its work and a new world emerges. The ashes of the past become the soil of the future. It is the prospect of this future that the Triassic period ultimately represents, and why it is so important in the history of our planet. It marks the beginning of a completely new era, the Mesozoic, also known as the Age of the Dinosaurs. This new era is synonymous with renewal on land and in the oceans. Many changes are bound to occur. Climate, fauna, flora, geography. Everything was turned upside down, but these changes were undoubtedly necessary for evolution to resume its course. The Triassic is a period when life renews itself, and many lineages will even reach us. Crocodiles, turtles, certain insects, and new corals and sea urchins are just a few examples. This heritage also includes the dinosaurs, of which birds are a part. These avian dinosaurs still roam our skies today, flying majestically overhead. But the Triassic is a complex equation made up of several phases, and let's not forget that the constitution of this new world and this heritage were built over millions of years. Let's go back to the Lower Triassic, around 250 million years ago, and try to understand together the main events that define this very special period. So here we are, 250 million years ago. The Permian is closing its doors, while the Triassic is opening wide. The extinction has left deep scars all over the Earth's surface, not least in the vast ocean that covers most of the globe. Neither Pangaea nor Panthalassa were spared the multiple upheavals that marked the Upper Permian. Life seems to have stopped there. After a few million years, however, the vegetation cover helped animals to repopulate the land. First of all, the few survivors of the Great Extinction were given free rein to conquer large territories on this vast land, which seems virtually untouched by ecosystems. They settle in new ecological niches left vacant after the disappearance of previous living beings. This gives them the opportunity to diversify at will and rebuild the living world. Rebuild, but also renew and diversify. Indeed, the surviving species are far from being the only ones to populate the Earth. New species enrich the various ecosystems. This is known as radiation or speciation. Species will evolve to adapt to their new environment and occupy the places left vacant since the chaos of the Permian. But before we meet these species, and I can imagine your curiosity and impatience, we need to know what we're getting into. Before we talk about the characters in our Triassic play, we need to know the context in which they evolve, if we are to understand all that's at stake. What's the Earth like at this point in our history? What's the weather like? Do you remember the famous continental waltz? The movement of tectonic plates and the effervescent activity of the Earth had led to the emergent lands coming together, uniting to give birth to a single supercontinent, Pangaea. At the beginning of the Triassic, the configuration of our planet was much the same as in the Permian. Panthalassa, the vast ocean, covered most of the globe, while Pangaea formed a single continent. From a vantage point nestled in the stars, we can see just how lonely Pangaea seems, almost fragilely isolated in the middle of this oversized expanse of water. Earth has never lived up to its nickname of Blue Planet more than at this time. From here, in the hollow of the C-shaped Pangaea, you can also see an ocean that appeared during the Permian, the Tethys Ocean. This paleo-ocean is teeming with life, a veritable marine nursery where numerous species were able to hatch and diversify. This was already the case in the Permian, but will continue to be the case in the Triassic. This ocean is one of the great protagonists of Triassic history. It was to evolve considerably over the course of the Earth's history, but particularly during this period. In particular, it rushed into faults such as the Hercynian chain, paving the way for the formation of the future Atlantic Ocean. We're in the middle of Proto-Gondwana, the southern part of Pangaea. No living beings, all is desert and dust. The climate is very harsh. It's easy to understand how hostile such an environment is to all forms of life, whether plant or animal. So how did dinosaurs settle on Earth at this time? Well, we need to qualify the statement about the prevailing climate and greenhouse effect. It would be a mistake to claim that the entire continent, except for the coasts, was arid and dry, even if it is true that many areas were very dry. While large parts of the continent are arid and do not benefit from the humidity of the air, there is one place on Pangaea that is quite different from the rest. To get a better idea, let's leave the Proto-Gondwana lands and head for the Triassic roof of the world, the Hercynian chain. This chain, like the Tethys Ocean we mentioned a moment ago, is an important protagonist in Triassic history. Its role is even crucial to the survival of flora and fauna. Without it, perhaps everything would have been different. The Hercynian chain, formed when Laurasia and Proto-Gondwana collided, sets the pace for climate and precipitation. This chain is so high that it's right up close to the clouds. It therefore has a major influence on the course of clouds, just like the Himalayas today. Blocked on one side, the clouds never flood the other side with their life-giving fertile water, leaving a barren, dry, and hostile landscape. Just what we saw in Proto-Gondwana. But let's climb those mountains and find ourselves on the other side, the Laurasia side. This time things look very different. There's plenty of humidity. Despite a climate that's as hot as ever, there's plenty of water and much greater humidity in the air. This humidity favors the development of vegetation and allows different species to occupy varied ecological niches. On this side of the mountain, life is therefore entirely possible, and even flourishing once the biological shock of the late Permian has passed, many years later. In short, on one side we find a warm, humid climate, on the other a hot, terribly dry one. As a result, a large proportion of terrestrial animals settled on the land, benefiting from the humidity. To get a better view of the world as a whole, let's take a look at the map of our present-day world. Here we can see the locations of fossil discoveries dating back to the Triassic period. We can clearly see that there are far more of them in the northern hemisphere than in the southern hemisphere, which corroborates this climatic division. In fact, the northern hemisphere corresponds to Laurasia. On these lands, vegetation has had a much better chance of developing, and thus favoring the development of fauna. Conversely, on the Proto-Gondwana side, in this hostile landscape, life seems to have had a hard time finding its place. Vegetation is virtually non-existent, and without it, the chances of seeing an ecosystem flourish are diminishing. Speaking of vegetation, let's take this opportunity to enter the Triassic forest to see how it managed to emerge from the crisis. By the end of the Permian, we could see that alongside spore-bearing plants, new plants had emerged. Reproduction by sporangia was not always possible, depending on the environment and climate. To meet new needs, seed plants had to enter the scene. After a timid appearance in the Permian, these plants developed more widely in the Triassic. Despite this, vegetation got off to a rather rocky start in the Triassic. The Permian extinction did not spare them. Sigillaria, lepidodendrons, Picopterus ferns, and the famous Glossopteris were devastated and disappeared forever from the terrestrial plant cover. However, while flora was affected by the Permian extinction, it was less so than the animal world, whether marine or terrestrial. As a result, plants were able to develop and grow more rapidly. Little by little, the formation of a shelter and nutritional resource for fauna seems to be taking shape. After just a few thousand years, we can say that vegetation is once again flourishing on Earth, offering a protective cocoon for any form of life wishing to settle there. In the northern hemisphere, conifers are gradually taking over the territory. We can see, for example, species of the genus Voltsia. This plant must have been quite similar to some of today's conifers, notably cypress or the Araucaria genus. However, it was never taller than a shrub. Initially bordering the coastline before growing a little further into the heart of the continent, these shrubs undoubtedly enabled some species to survive this transitional period after the Permo-Triassic crisis. They were also able to create mangroves in certain parts of the coastline, providing a less arid climate more conducive to the growth of rich, diverse ecosystems. Now that we're standing at the foot of these Voltzias at the mouth of this river, why not continue our investigations and discover what the oceanic universe has to teach us? The marine world bore the brunt of the Great Extinction. Scientists estimate that nearly 95% of marine species have disappeared. Let's see how life is gradually returning to this aquatic universe. So here we are in the middle of the Tethys. The water's great, isn't it? The temperature is ideal for taking a dip and immersing ourselves a little deeper. Things have changed in the ocean since the blessed days of the Permian. The landscape, first ravaged by extinction, has once again seen a flourishing and rich aquatic life. But not all species have made it this far. The Paleozoic was the golden age of trilobites. Proliferating in abundance in all the world's oceans, they gradually declined, disappearing completely at the end of the Permian. After the Permo-Triassic crisis, coral reefs also struggled to recover. Hexacoralliar corals, i.e. modern corals, took advantage of this vacancy to the benefit of tetracoralliar corals. The Mesozoic was also known as the Golden Age of ammonites and sea urchins. Ammonites are considered stratigraphic markers. This means that given their great diversification and proliferation through the ages, scientists are now able to determine the age of the rock in which a fossil of one of these ammonites is found. Nicknamed sea hedgehogs, sea urchins now populate shallow seas alongside starfish. In the rest of the water column, life is equally varied. Indeed, in this seascape, in addition to ammonites, sea urchins, and several thousand varied mollusks, we also find a species, or rather a group, that we have already encountered on our previous trips, notably in the Permian. These are the chondrichthyans, distant cousins of sharks. These primitive sharks, if we can put it that way, gradually become the kings of the oceans during the Paleozoic. Chondrichthyans are divided into two subclasses: the elasmobranch subclass, to which rays and sharks belong, and the holocephalon subclass, to which chimeras belong. Holocephalons have their upper jaw completely attached to the neurocranium, whereas this is only partially the case with elasmobranchs. Another notable physical difference is in the gill openings. These are of two types: a single opening in holocephalons and 5 to 7 gill slits, which are very characteristic of sharks and rays. After the Great Extinction, many chondrichthyan species are in decline. However, their demise is far from certain, as some of them will manage to survive despite the obstacles they face. Their ability to occupy the deep sea is undoubtedly what enabled them to survive during this difficult period. According to the fossil record, these chondrichthyans did not return to the surface until 35 million years later. But more on that later. Some chondrichthyans continue to evolve during this period. Xenocants can be found in this aquatic world. A distant cousin of the shark, the xenocant silhouette bears some resemblance to our modern-day sharks. It does, however, have more and differently shaped fins on its flank. It also has a long spine at the top of its head. As far as this spine is concerned, scientists can't say what its precise purpose is. However, one hypothesis is that it could be a predatory tool, rather like the venomous stingers of modern-day stingrays. Other chondrichthyan species have also found their way into the oceans. The most common of these in the Triassic period are the hybodonts, which we'll be looking at straight away. These evolved considerably over the period. At the beginning of the Triassic period, they were only a few tens of centimeters long, so they preyed on prey at the height of their capacity and opportunity. But from the Middle Triassic onwards, we discover species that are far more generous in terms of size. Some now easily reach 3 meters or 10 feet in length. As you'd expect, their prey has changed too, and they've adapted to a completely different environment. At first, they tended to prefer freshwater, but little by little they've acclimatized to the salty waters of the coast. As their prey became much larger, their dentition evolved. In Hypodus, we can observe teeth cut to tear. They are perfectly sharp and razor sharp. In others, such as Tribodus, we're faced with another type of dentition that could be described as crushing. Previous sea urchins and ammonites have undoubtedly paid the price. Thanks to their respectable size, swimming ability, and sharp teeth, hybodonts have risen to the top of the food chain, but they're far from alone, sharing the top spot with other sea monsters. The warm, shallow waters of the Tethys offer an extraordinarily rich marine world. As we have already seen, some species have acclimatized quite well to their new world, but they are far from alone. Other species have even benefited from one of the greatest radiations, so to speak, of the entire Mesozoic. These are marine reptiles. These land animals were among the first to reach the ocean to adapt. The continent, as we've seen, can be very dry, and therefore a rather hostile terrain for terrestrial life to flourish. Their preferred playground is the coastline. Indeed, they are most numerous in coastal areas. Some are aquatic, others semi-aquatic, while others still raise questions, like this, Canistropheus. Its name means long vertebrae. Now you know why. This Mesozoic phenomenon was first discovered over 150 years ago in Germany. Imagine how big the surprise must have been when paleontologists unearthed a skeleton nearly 6 meters or 20 feet long, with a neck that alone measures almost 3 times the size of its body. Conversely, it has a small head and a modest tail. This reptile has long been the subject of scientific debate. At first, it was thought to be semi-aquatic, then predominantly aquatic. It's its long, stiff, disproportionate neck that raises questions. Unlike similar species such as the plesiosaurs, its neck was so rigid that it could neither bend nor twist. Under these conditions, its movements and hunting strategies must have been difficult. Still, scientists have managed to unravel some of its mysteries. It feeds mainly on small fish, and its neck is its best fishing asset. It can attack by surprise and hunt in open water, although it is a poor swimmer, or from the bank by plunging its long neck to the bottom. Convenient for fishing, but that long neck was probably its undoing. According to recent studies, this long, stiff neck made Tanystropheus an easy prey for predators. It was decapitated in a single bite. At least that's what the fossilized remains have shown. There is a clear trace of dental perforation, and the neck is broken in a single backward fracture. Importantly, the results also show that the attack was carried out from above, i.e. in the water. He's not a good swimmer, he's not dexterous in the water, and he's far from fast. What's more, he can't control and direct his neck to protect himself. Attacking from above, knowing that a single bite is fatal, he has no way of escaping. Given the reptile's size, not just any predator could take on such a behemoth. 3 suspects are in the running. Most are piscivorous, but they're not averse to eliminating a potential competitor. Let's find out together. The first is undoubtedly the Nothosaurus giganteus. It measured almost 7 meters or 23 feet in length. It belongs to the diapsids. After a timid attempt in the Permian, diapsids invaded the marine environment, and Nothosaurus was one of the most important of them. With their short webbed feet, Nothosaurians lived like today's seals, returning to land to rest and lay eggs. Their elongated necks ended in flattened heads. The jaws bristling with long, sharp teeth leave no doubt as to the animal's diet. Contrary to popular belief, they are not exclusively aquatic. Indeed, to lay eggs, for example, it undoubtedly travels to the coast. The Nothosaurus family is probably the most speciated marine reptile of the Triassic period. During this period, almost a third of all species belong to this group. Let's take a look at Cymbospondylus. It belongs to the ichthyosaur group. Ichthyosaurs were quite numerous in the lower Triassic, but this group declined somewhat in the middle Triassic. They were confined to the coastline and were rather modest in size, their diet being limited to animals with shells. Cymbospondylus, on the other hand, is better adapted to the open sea and moves easily away from the coast, so it's easier for them to get by. It looks a bit like our modern dolphins and measures between 6 and 10 meters or 33 feet in length. With its tail accounting for around half of its total length, scientists believe this animal had an undulating swim. Thanks to its tail, it was able to gain speed and even accelerate to surprise its prey. It hunted mainly schools of fish, but perhaps he's not entirely innocent when it comes to the Tanystropheus attack. Finally, there's Helveticosaurus, another marine reptile from the Triassic period. With its long, flexible tail, it too had to swim sideways. It is, however, a little smaller than our previous reptile, measuring around 2 meters or 7 feet. Even so, it's still pretty formidable. While many of the reptiles we encountered have rather elongated, narrow skulls, this one has a robust, wider one. Its rather broad, powerful neck and sharp jaw made it a great marine predator. Its long, curved, conical teeth took on its victims with disconcerting ease. Perhaps our Tanystropheus had the unfortunate experience. These three great marine reptiles are far from the only ones to roam the seas. In fact, this is why chondrichthyans have gradually lost their place in the ocean, although they have not disappeared. In another genre, I'd like to introduce you to Placodus, a sauropside that belongs to the Placodont family. Placodonts are marine diapsids whose bodies are protected by a carapace of enlarged ribs. In some species, these enlarged ribs are even fused together. Placodonts belong to the groups that flourished in the Triassic period. They diversified extensively during this period. Placodus is quite different, as you can see, from our long-necked reptiles. Measuring 2 meters or 7 feet long on average, it is rather stocky and has a relatively short neck and legs. Placodus is equally at home in the water and on land. He's not very fast, but he does pretty well and is far from lagging behind when prey presents itself. Speaking of prey, Placodus is particularly fond of mollusks and crustaceans. Its teeth are devilishly efficient, a veritable shell crusher. In fact, its large cobblestone-shaped teeth crush the shellfish it plucks from the seabed or rocks, thanks to the flattened teeth at the front of its jaws. Nothing can resist it. Now let's take a look at another marine reptile. You can't leave the ocean without admiring the famous Plesiosaurus, undoubtedly one of the most emblematic reptiles of the Triassic period. Recognizable by its barrel-shaped body, swimming legs, long neck, and small tail, the plesiosaur fascinates fans of prehistoric Mesozoic animals. This group of marine reptiles is very popular, and no doubt fueled the legend of the Loch Ness Monster. He is also known for his epic battles with ichthyosaurs, if the breathless literary works of the 19th century are to be believed. When he wasn't fighting to preserve his place and preserve his hunting territory, he was attacking schools of fish, his favorite delicacy. Its long, perfectly flexible neck enabled it to cross schools of fish. To capture its prey, it used its long, sharp teeth. Let's continue with another ichthyosaur. This time, it's a Myxosaurus. It's one of the smallest marine reptiles we've seen so far. It measures around 1 meter or 3 feet and weighs just 20 kilograms or 45 pounds. Its dolphin-like, slight-arched body is equipped with a dorsal fin, pectoral fins, and a pseudo-caudal fin. Despite having longer front flippers than rear ones, it seems that our ichthyosaur was rather slow. But that didn't stop it from teasing fish when it was hungry. Its many sharp teeth testify to its predatory abilities. Myxosaurus has much in common with other ichthyosaurs. First of all, they are all reptiles that have returned to the aquatic environment and no longer have any connection with dry land. In fact, they give birth to their young in the open sea. Secondly, they too had to come to the surface to breathe. And yes, contrary to popular belief, they do have lungs, not gills. So here's what we can say about marine reptiles. As we have seen here, a far from exhaustive list of the members of this group. As well as being very diverse, they are also very present, especially in the Tethys, but also very numerous. Their sheer numbers and tremendous radiation no doubt have their origins in the rising waters of the Triassic period. As we saw earlier, the Hercynian chain occupies a strategic position on the continent of Pangaea. But there's a small detail that we haven't mentioned yet, but which is of major importance here. On the western flank, a rift was created between the mountain range and the Tethys. Since then, the Earth's activity and the movement of tectonic plates have caused this fault to widen more and more. Water infiltrates and gradually covers part of the land along the fault. As the water advances, the fault will eventually fracture completely, splitting the continent in two, with the opening of the North Atlantic Ocean. But let's get back to our subject, marine reptiles. This rise in water level is beneficial to them. They are taking advantage of the windfall and expanding their territory. They fill in the gap and settle along the coastline. Food is plentiful, and there are no real predators competing with them. All the lights are on to occupy new ecological niches. They thrive, but they also evolve rapidly. This is why this extraordinary group of animals is said to be undergoing a major radiation phenomenon. If there are so many predators, it's because prey are also present. The fish we're about to see are undoubtedly part of the menu of one of these reptiles. Perlitus, for example, is an actinopterygian fish. Actinopterygians are bony fish whose fins are supported by rays. It measures around 15 centimeters or 6 inches. Alongside Perlitus, another actinopterygian fish can be found in the water column, Ababa satrania. The shape is a little different, and it is slightly longer, around 20 centimeters or 8 inches. These fish are found alongside another kind of aquatic animal. Encrinus is in fact a crinoid. Crinoids are echinoderms such as the sea star or sea urchin. Without leaving the aquatic world altogether, but swapping the marine world for banks and marshes, we can also encounter large amphibians, just as fearsome and feared as our previous marine reptiles, within their own ecosystem. The banks and coasts, like the marshes, benefit from lush plant cover. They therefore abound in insects and small prey of all kinds that can satisfy the appetite of our amphibians. Meet Stenatosaurus, a labyrinthodont amphibian. Labyrinthodonts are large salamander-like amphibians. Some of them were giant salamanders, though, as Stenatosaurus could well have measured between 2.5 and 3.5 meters, or up to 12 feet. Their name, labyrinthodont, comes from the shape of their tooth enamel. The contact surfaces of the teeth form a kind of labyrinth. Today, an animal of this size would be very impressive and particularly frightening, despite its gentle salamander-like appearance. In the Triassic period, it appreciated marshy environments and undoubtedly hunted small fish. Despite its incredible adaptability, it will have a hard time competing with the arrival of crocodiles in the near future. What do you say we leave the wetlands behind and head a little further inland to discover the wildlife that inhabits the continent? As we mentioned in the introduction, for Triassic fauna, the first act of the period was rather difficult to get through. The stigmata of the Great Crisis are still very present, and it is initially the species that survive the crisis that populate Pangaea. These survivors included archosauromorphs such as the Rosocians and Sarasuchus in particular. It wasn't until the Middle Triassic period that the evolution of these archosauromorphs became truly significant, as the future archosaurians gave rise to pterosaurs, crocodiles, and dinosaurs, making up a large part of the Mesozoic animal population. As we have seen, at the very end of the Permian, a few reptiles tried their hand at flight, or rather gliding through the air. Initially, they flew only short distances, enabling them to move from tree to tree without risking their lives on the ground. Predators are numerous and dangerous at the foot of trees. However, these reptiles also benefit from radiation and are able to compensate for this apparent danger. This radiation, or speciation, whichever term you prefer, enables some species to occupy new ecological niches and adapt to different environmental conditions. Here, it's the numerous predators on the ground that require adaptation. At the same time, insects have flourished, particularly in the upper part of the forest, the canopy. These insects form a new food reserve, and thus an ecological niche that is currently unoccupied or only marginally occupied. These new reptiles of the sky will find both protection and a source of food in flight. Archosaurs gave rise to a new lineage, the pterosaurs, the famous flying reptiles. No, they're not dinosaurs. Pterosaurs are indeed reptiles, but they have large wings made up of several membranes. One is attached to the fourth finger of their forelegs, another is between the wrist and the trunk, and the third is attached from the thigh to the tail. The first and last are not always perceptible, depending on the representations imagined by the artists. In some species, however, these small membranes are clearly visible. The largest, which forms the wing proper, is very distinctive. Among the pterosaurs, we can admire the flight of Eudimorphodon and Priondactylus, the very first sky gods. In fact, here we're no longer dealing with a gliding mode of travel, but rather with the beating of wings. That's why we're talking about flying reptiles, not gliders. In the Triassic, there were three main families of pterosaurs: Campylognathodidae, Anurognathidae, and Dimorphodontidae. Eudimorphodon is the oldest known to date and belongs to the Campylognathodidae. It seems that this family did not continue its evolutionary process after the Triassic period. By contrast, the Anurognathidae and Dimorphodontidae families continue to thrive and evolve. The most primitive species would be Priondactylus. We can see, for example, that its legs and even its wings are relatively short. Others, such as Rhamphorhynchus, appear to be more advanced. At least their speciation seems more obvious. The teeth of these pterosaurs are more differentiated. Rhamphorhynchus means jaw beak. It's easy to see why, given the length of their teeth. In addition to their size, they are also sharp and curved forward, a very useful set of teeth when it comes to harpooning its prey in flight. The Dimorphodontidae family includes the Dimorphodon genus and the Petanosaurus genus, which means winged lizard. According to scientists, as pterosaurs evolved, two main subgroups emerged: the long-tailed rhamphorhynchoids and the pterodactyloids. The rhamphorhynchoids are the first to arrive, along with Eudomorphodon and Petanosaurus, which we saw earlier. Among the oldest known pterosaurs is Austriadactylus. It belongs to the Cambrian family. Austriadactylus has an estimated wingspan of around 1.2 meters or 4 feet. That may sound impressive, but compared with future pterosaurs such as Quetzalcoatlus, an animal weighing almost 250 kilograms or 550 pounds, and with an 11-meter or 36-foot wingspan, it looks pretty small. The Middle Triassic was a rather flourishing period for both marine and terrestrial fauna and flora. However, the transition from the Middle Triassic to the Upper Triassic was not a smooth one. A mini-crisis, so to speak, gradually set in. Many species declined, while others took advantage of the gap to move into these new ecological niches. We saw the rise in water levels a few minutes ago during the Middle Triassic. This time, the level is gradually dropping, bringing with it its share of consequences, dramatic for some and beneficial for others. Scientists are not yet in a position to assert anything, as they unfortunately lack sufficient data on the subject. However, and this is of course conditional, it could be that the hypothesis of the regression of the ocean is at the origin, or at least one of the possible reasons among others, for this crisis during the Triassic period. If this were true, it could be that the shrinking of the epicontinental zone, by which we mean a sea bordering the continental shelf, would have upset the established order of coastal-dependent animals. This hypothesis is supported by the fact that pelagic animals, i.e., those that swim or float on the high seas, suffered very few negative consequences from this regression of the waters. They have probably simply expanded their territory. Those that depended on the coast, on the other hand, are finding it extremely difficult to survive. Only coastal animals such as Nothosaurus have been fully affected by this change in environment. In marine reptiles, the established order was totally reshaped. These predominantly coastal animals are gradually being replaced by pelagic animals, i.e., those that take advantage of the open sea and the water column. Coastal marine reptiles are not the only ones to suffer the consequences of this micro-crisis. Chondrichthyans were also severely affected by the intermediate crisis that weakened the transition from the Middle Triassic to the Upper Triassic. Many of them are benthic animals. As the waters receded, the lack of oxygen made it difficult for these species to acclimatize to deeper or more remote areas. Lack of food and anoxia will be the death knell for these species. All of them? Not quite. Remember, when we talked about chondrichthyans, we saw that a small handful of them had, unlike the others, finally found shelter in the deep sea. So they came through the crisis with flying colors. However, before they could go a little further to the surface, as their ancestors did at the time, it would take a long, slow evolution of almost 35 million years. Hybodonts, for example, are among the chondrichthyans that adapted perfectly to the waters of the Triassic period. They lived through these 50 million years, enjoying the oceans, yes, but with fear in their stomachs. They lived in the same geographical zone as the imposing marine reptile Liapleurodon, for example, which could measure up to 7 meters or 23 feet. Hybodonts, far from being alpha predators at the top of the food chain, were the prey of large marine reptiles. The late Triassic also saw the appearance of so-called modern sharks. The main difference between the so-called primitive sharks and the more evolved ones is their backbone. Do you remember the swimming style of the chondrichthyans we've met so far? No? Then let me refresh your memory a little. Most of them had what we call an undulating stroke. It's still quite effective, but it's far from being very efficient. Now, do you know why these animals swam this way? Contrary to what you might imagine, it had nothing to do with their fins. In fact, it's the spine, and more specifically, the structure of the spine itself that's the key. Their spine is cartilaginous, and therefore very flexible. The undulatory mode is therefore ultimately the only possibility. Modern sharks, on the other hand, have a calcified spine and are therefore much more rigid. Swimming is much more efficient, and above all faster, as they can propel themselves and better manage their trajectory. These sharks will therefore be able to adapt and conquer new marine territories. To conclude the subject of species in decline and those benefiting from radiation, let's talk about ichthyosaurs. Ichthyosaurs are undoubtedly the ones that are doing best in the end. We met some of these species earlier. They managed to make the most of the deep sea, and are, for the time being at least, safe from harm. This group is growing and diversifying. First appearing millions of years ago, they crossed the Jurassic and even the Cretaceous. They were thus present throughout the Mesozoic. Quite a feat when you consider how many upheavals and crises there were. In addition to rising sea levels and the complications faced by marine species, the arrival of the Upper Triassic heralded drastic climatic changes. If a fragile equilibrium seemed to have been achieved during the Middle Triassic, it is now beginning to fracture. In the Late Triassic, Pangaea fragmented a little further, and intense volcanic activity in areas such as Morocco and New England signaled the beginning of the opening of the North Atlantic. The average global temperature is 18 degrees Celsius, or 64.4 degrees Fahrenheit. It was 17 degrees Celsius, or 62.6 degrees Fahrenheit, at the beginning of the Triassic period. Terrestrial activity, particularly plate movement, brings with it many geological, climatic, and therefore biological changes. But this doesn't prevent certain species from continuing their gentle evolution, almost serenely. The Mesozoic is a fascinating period. From an early age, children are fascinated by the animals of this period. Dinosaurs are as captivating as they are frightening. Animals 1,000 miles from those we know today, inconceivable in our own time, of such extraordinary sizes and morphologies that they seem to have sprung straight from our imagination. And yet, they're very real, and even walked the earth before us humans. It's these emblematic animals of the Mesozoic era that have made it so popular with the general public. Their story begins in the Middle Triassic, but it's mainly in the Upper Triassic that a spectacular diversification takes place, to make a striking entrance on the Jurassic scene a few thousand years later. Let's go back to their beginnings to understand their evolutionary process. In the animal world of the late Paleozoic and early Mesozoic, amphibians and mammalian reptiles gradually gave way to diapsid reptiles. Among the latter, as we have seen, archosaurs underwent significant adaptive radiation. They gave rise to groups that disappeared at the end of the Triassic, such as the phytosaurs, attosaurs, and the Rossochians, as well as the crocodiles and the pterosaurs that we recently left behind. But the ones we remember most are undoubtedly the dinosaurs. Their history begins with the dinosauromorphs. Lagosuchus, Merosuchus, and Lagerpeton are all reptiles with the potential to start the dinosaur line. Lagosuchus is a lightly built archosaur, remarkable for its long, slender legs and well-developed foot. Here we see the characteristics of the first dinosaurs taking shape. It is, however, much smaller than its descendants. It measures just 40 centimeters or 16 inches in length, and weighs just 100 to 200 grams. Its name means crocodile rabbit. This name perfectly defines its physical attributes and abilities. Carnivorous, it preys on small prey, such as lizards, but is also fond of insects. Although it moves around on all fours most of the time, it can also rise easily on its hind legs and even run. It is therefore an agile predator, able to use its speed to hunt prey and escape from larger predators. Let's take a look at Merosuchus. Clearly a member of the dinosauromorph clade. He doesn't yet have a hole in his skull, between the eye socket and nostrils, behind each eye socket, or the famous hole in the hip socket. It does, however, have an elongated pubis and the trochanters, a kind of protrusion on the anterior femur, characteristic of dinosaurs. Research and studies are still going on today to get closer every day to reality, and above all, to the truth about the history of our planet and its past inhabitants. According to recent studies, other species such as Silosaurus are probably even closer to the first dinosaurs than Merosuchus. With the passage of time, it's always difficult to be definitive about such ancient origins. Speaking of Silosaurus, a rather astonishing anecdote was revealed in a 2018 article in the journal Historical Biology. It seems that paleontologists were able to demonstrate through the study of its skeleton that juveniles begged for food in the manner of fledglings with their heads raised and mouths wide open. This is a nod to our modern birds, which we might describe as avian dinosaurs. Now let's take a look at the final member of our dinosauromorph trio, Lagerpeton. Measuring 70 centimeters or 28 inches long, his body is built for running. It has elongated hind legs and a highly developed tibia. There are also some similarities with early dinosaurs, or at least characteristics that could have given rise to the dinosaur lineage. One of Lagerpeton's astonishing abilities, based on the study of its toes on the hind legs, is that it was undoubtedly a jumping animal, or at least capable of this little feat. Knowing that it was certainly an insectivore, this type of ability would indeed have been an asset when hunting insects. So that's what we can say about the first dinosauromorphs. If we follow the thread of our history and the evolutionary processes of these different species, we can see that things were moving very fast in the animal world at this time. While the first dinosauromorphs were developing, pterosaurs occupied the skies and marine reptiles invaded the oceans. Over thousands of years on land, territories were divided between dinosaurs and crocodilians, and at first the dinosaurs clearly had the advantage. They developed faster and more extensively than the crocodilomorphs. Dinosaurs were able to radiate so rapidly because they easily counter crocodiles and seem better adapted to their environment. First of all, they are bipedal predators with vertical limbs. Unlike crocodiles, which are quadrupeds with lateral limbs, they are much livelier, and above all more mobile when hunting prey or even fleeing a larger predator. Secondly, contrary to popular belief, dinosaurs appear to be warm-blooded. This metabolism allowed for a more active lifestyle. The rest of history, however, ultimately favored crocodilians, which are still with us today, while non-avian dinosaurs died out at the end of the Cretaceous. We'll come back to the subject of crocodiles a little later in our video, but for now let's return to the subject that interests us here, the Triassic and the birth of the dinosaurs. Their rise, development, and in particular their diversification were very rapid. As early as the Triassic period, just a few million years after their appearance, we can already see the appearance of the two great lineages that will define the classification of this great family of dinosaurs. The latter gave rise to the theropods, which include the large carnivores, but also birds. To understand what characterizes and differentiates these two groups, we need to look at their skeletons. Saurischian means lizard hip, while ornithischian means bird hip. The pelvises of both, as shown here, are quite distinct. Saurischians are therefore dinosaurs with a pubis facing forwards, unlike ornithischians, whose pubis faces backwards. Paradoxical as it may seem, it was not the ornithischians, the bird hips, that gave rise to the avian dinosaur clades. Birds, in fact, originated from lizard hips, the Saurischians. Now that we know a little about the two great dinosaur lineages, it's time to meet our first specimens of the genus. This small Upper Triassic tetrapod dinosaur is 222 million years old. It's true that when you think of the extraordinary sizes that later Mesozoic species would sport, it's hard to imagine that this little being of just 1 meter, or 3 feet long, 30 centimeters, or 12 inches high, and between 1 and 5 kilograms, was part of this extraordinary family. And yet, it's one of the very few dinosaurs the Earth has ever known. Bipedal, it has long hind legs but short arms. It has large clawed hands, a long slender snout, and a tail. Don't be fooled by its name, which means elegant jaw. It has many small teeth, and judging by its teeth, is a carnivore. It feeds on insects, lizards, and other small prey. It can also be a scavenger. This little dinosaur prefers marshy areas. It has established its territory in this vast area where food is abundant, and thanks to its mobility, it can easily conquer an ecological niche that can still be exploited by new predators. Let's take a look at another old dinosaur, so to speak, with the study of plateosaurs. From the Upper Triassic onwards, dinosaurs began to reach impressive sizes. with the genus Plateosaurus, we're a long way from being able to maintain the appellation small dinosaur in our description. Estimates put its average length at 8 meters or 26 feet. It weighs around 4 tons. With its thick, robust bones, this is a rather massive dinosaur. Skeletal studies show that this type of dinosaur could move around on all fours, but could also stand up on its hind legs if necessary. They are robust but also very powerful. Why were they so powerful? No doubt to feed on the leaves and the trees. Yes, our gentle mastodon is not a carnivore, but a herbivore. Its serrated teeth enable it to crush the leaves it eats. To help with his digestive process, he also swallows stones, gastroliths, to better crush the food in his stomach. Another dinosaur, this time a carnivore, lived in what is now South America. This was Herrerasaurus. Herrerasaurus occupies a fairly large territory in valleys where a river meanders through the middle of the land. This precious commodity attracts many animals looking for water, and therefore potential prey. It measures just over 3 meters or 10 feet long on average, and weighs between 200 and 300 kilograms, or between 440 pounds and 600 pounds. If he's not so heavy for such a respectable length, it's because his bones are long and hollow. At the time, it was undoubtedly the largest terrestrial carnivore. It attacked almost all the vertebrates in its ecosystem, including rhynchosaurs, diconodonts, and etosaurs. A biped, it had powerful hind legs, short thighs, and long feet. This type of silhouette suggests that it was probably a good runner. It also has short arms equipped with sharp claws for lacerating prey and tearing flesh. Its sharp, curved, razor-sharp teeth were perfect for killing its victims. Thanks to its articulated jaw, once the prey is seized, it can hold it firmly in its mouth. Our Herrerasaurus shares its territory with other predators, notably a crocodile-like quadruped like Sarasuchus. Its legs are not on its sides but under its belly. This makes for more skillful movement. It averages 7 meters or 23 feet in length and is a feared carnivore in the valley. Its teeth are large, curved, and serrated, making for a good grip and deadly damage. Let's take advantage of the discovery of this Sarasuchus to talk about the crocodilomorphs, which we have so far neglected in favor of dinosaurs. Crocodilomorphs appeared around the same time as dinosaurs. While the latter underwent a meteoric rise in radiation, the crocodilomorphs are still very important. Crocodilomorphs diversified extensively, starting in the Triassic period. However, not all crocodilomorphs took the form we recognize today. The first crocodilomorphs, undoubtedly the Sphenusuchians, look more like ferocious greyhounds than crocodilians in the strict sense. Small in stature, they are slender and slender. The fact that they are quadrupeds with their hind legs longer than their front ones gives them a slightly arched, slightly built appearance. In addition to their modest size, the first crocodilomorphs were also rather active, compared with the way today's crocodiles look. While some species will find it difficult to adapt to the various changes that will take place on Earth over the coming thousands of years, other, slow-growing crocodilomorphs will make it through the ages. Even today, this characteristic still defines crocodiles, which take several years to reach their final size, Let's close this crocodilian parenthesis and return to our famous dinosaurs. Among the oldest of them, we can also mention the Euraptor, as well as being one of the oldest. The Euraptor is also one of the smallest. It measures just 40 centimeters or 16 inches high, and is about 1 meter or 3 feet long. According to skeletal analysis, the Euraptor was a small, skillful carnivore. Its long legs enabled it to run fast in pursuit of small prey such as lizards. At the end of its long neck, its slender skull housed an army of small, sharp teeth. Another popular Triassic dinosaur was Colophysis. Rather slender and agile, this carnivore measured up to 3 meters or 10 feet in length, for an average of 30 kilograms or 66 pounds. It is therefore rather slender. Using its curved, crenulated teeth, it hunted fish and insects. Paleontologists have unearthed numerous fossils of this species, notably in Arizona and New Mexico. The study of these fossils has revealed a number of clues as to how these dinosaurs lived. Firstly, they probably lived in groups. There are 2 advantages to living in a herd. Group hunting is often more fruitful, and group protection is facilitated by numbers. However, despite the emergence of new clades and extraordinary lineages, despite the ability of certain species to adapt to a complex environment, despite the apparent calm and exponential diversification, once again the world is heading for chaos. The Triassic remains the only period in geological history framed by 2 major crises. While the beginning of the Triassic was built on the ashes of the Permian, the end of the Triassic did not have a more glorious ending, with a major new crisis that would constitute a real fracture between the Triassic and the Jurassic to come. At the end of the Triassic, there was intense volcanic activity, and let's not forget that the Atlantic Ocean was opening up. A few small pieces of land appeared with this lowering of the water level. This newly hatched archipelago was the birthplace of the future Europe. Volcanic eruptions are numerous and intense, releasing massive quantities of gas and dust. The Earth continues to heat up. Another fracture, other than that of the Hercynian chain into which the Tethys rushes, takes shape at the ridge that links western Gondwana to eastern Gondwana. In addition, several medium-sized asteroids will strike the Earth. Impact craters, such as the Manicouagan crater in Labrador, with a diameter of 100 kilometers or 62 miles, bear witness to this. A climatic and geological upheaval was all it took for a biological upheaval to sweep the Earth once again. The pre-established order is shattered. Nature will once again need perseverance, tactics, and courage to rise from the ashes. But that's for another story.